In the previous video, we learned how to build a ripple carry adder, but we also realized that its running time is not so good. It can take a long time to do just one addition. Now we want to come up with an interesting design to be able to overcome that limitation. Okay, so let's just start by revisiting what the ripple carry is. You have, let's say, a ripple carry adder of 4 bits. What's going to happen is that you get your first carry in, you're going to generate your first carry out, and this is going to just step by step ripple through. And that's the problem, right? Because this is going to create a delay. You won't get this the correct value for C3 until everything here has finished. How could we fix this? The basic idea here is that if you can make each of these logic gates that we have here more complex, then you could perhaps do more of the computations at the same time. So what we would like to be able to ideally is to remove these dependencies between the 4 different gates. Somehow came up with some piece of hardware that will generate for us all these carry-ins for the second, third, and fourth gate at the beginning. So in the beginning, we want to just run this logic right here, generate all the bits, and then let each of the 4 adders do their jobs independently from one another, so they can now work at the same time in parallel. Why? Because they all have the input that they need. Of course, we have to spend a little bit of time on this, but perhaps we can gain more by making the 4 things independent. Now let's think a little bit about how we would do that. So let's start with C1. You can see that C1 is the OR of 3 ANDs. So let's look at the first AND here. For example, right here it's just AND of A and B. And this A and B are A0 and B0, right? Because these are what we are sending to the very first gate. This is A1, B1, this is A2, B2, this is A3, B3. Okay, so let's see what's C1. C1 is A0 and B0, or A0 and C0, or A0 and B0 and C0. Okay, so I'm using a very standard notation here. You should have seen before. Standard notation. Okay, so we have the value of C1, and this is just basically implementing this logic. The next thing we want to do is simplify this a little bit. We take this, and I'll take these 2 C0s and I'll take them out. Right, I can factor them out. So I get A0, B0, or C0 and A0 plus B0, A0 or B0. Okay, so AND can come out of these. You can factor it out. You have learned that before, and that's all with it. Okay, so that's just a simplification. Now, this yellow logic that we created, that we designed here, has to be able to output this. Okay, it has to be able to output this. And so, I mean, computing this is not so difficult, right? It's just, a bunch of ANDs and ORs, not so many of them. So let's assume we can do it. But let's keep going and get to C2, because C2 is going to be a little bit more difficult. C2 is going to be A1, B1 plus A1, C1 plus B1, C1. However, the problem, and you can still use the same trick, you can call it A1, B1 plus C1 uh, multiplied by A1 plus B1. So far so good. The issue is that the input to it is C1. And in this logic, we did not want to depend on the calculation of C1. So I don't want to wait for C1 to be calculated. So I want this yellow logic here to also compute C1 for me automatically. Can that be done fast enough? Okay, so let's just replace C1 here with its correct value that we had computed here. So C1 is going to be A0 B0 plus C0 A0 plus B0 multiplied by A1 plus B1. Now you can see that these equations are getting a little bit complex. So I'm going to do something simple. I'm going to define a name G0 and another name P0 for the and for the or. So let's just call GI is AI and BI, and PI is AI or BI. These are just just a definition. So with that definition, I can write C1 now a little bit more neatly as G0 plus C0 P0. Alright, so my notation became a little bit neater, and I can do the same thing here. I can write this as G1 plus this whole thing is just what we had written here. So I'm going to copy that over, G0 plus C0 P0, and the last term is going to be simply P1. And if I do this sort of AND, if I take this AND inside, I'm going to be left with G1 plus P1 G0, so I'm going to write it as G0 P1 plus P1 P0 C0. Now why is this a nice equation? Think about computing this. For computing this, you need C0 that which you have at the beginning. C0 is the only one that you have in the beginning. You need these P0s, P1s, and G0s, right? You need all of those. But those you can also compute in the beginning, right? So at the start of this function, at the start of this this yellow logic, you can very easily compute all of this in parallel to each other. They do not depend on each other. And after that step, I can immediately compute this quantity, which is C1. So I don't have to, which is C2. So I don't have to wait for C1 to compute C2. I can compute it independently from C1. Okay, that's very nice. And you can do the same trick again and again. Let's do it for C3 and C4. For C3, you have A2, B2 plus A1 plus B1, so A2 plus B2 multiplied by C2. And if I apply the same logic here, I'm going to get G2, which is this first term, plus P2 multiplied by C2, but C2 is just this, so I'm going to replace it with that. And if I take that P2 inside and multiply it by everything, I'll get G2 plus G1 P2 plus G0 P1 P2 plus P2 P1 P0 C0. Okay, again, this equation is long, but you can compute all of this right after you have computed all these quantities. So you don't have to wait for C2 to get C3. If you do the same trick for C4, you might have gotten the hang of it at this point. You're going to be left with something like this: G3 plus P3 G2. Let me, for consistency, write it as plus G2 P3 plus G1 P2 P3 plus G0 P1 P2 P3 plus P3 P2 P1 P0 C0. You can do the same exercise and see that this is correct. So now we have computed C1, C2, C3, and C4, all of them independently from one another. In here you do not need the previous C's. Here you do not need C2 or C1. Here you do not need C1. Here you need C0, but that's okay because C0 is given to us from the beginning. Okay, so now that we have seen this, all these calculations, we really do know at this point how to compute, how to design this logic here. You have everything that you need, but let's just draw one as well, just so that we see it better. So I just copied all those equations to this page so that we can see things easier. So the first thing that you notice we are going to need is to compute G and P for all the A's and B's. So if let me use green. If this is an A, this is a B, we need to be able to compute their OR and their AND, which will give us the P and the G. We are going to do this in parallel for all 4 inputs. So I'm going to take this and I'm going to copy paste it. Okay, so we have all the 4 G's and sets of G's and P's calculated. Let's say this is that logic that I was drawing before. In addition to all of these, you are going to have the C0 also as input. Now for each of these, I'm going to then compute the C's now, right? So let's start with C1. For C1, what you need to do is to simply just AND C0. I'm going to take C0 across so that everyone has it. And then I'm going to take this C0, compute its AND with P0, and then you compute the OR of that with your G0, and you have calculated C1. The end of the story. There is nothing else you need for C1. That was quite easy. Now for C2 is going to be slightly more complex. Let me add all these indices. Now for the next one, we are going to need to compute this. So let's make an AND of P0. We're going to need P0 everywhere as well. So I'm going to take it. Take P0, P1, and C0, and compute their AND. I need one more AND, which is of G0 and P1. Okay, I have P1 over here. So you take that P1 and you AND it with this G0, which we also need to take from everyone. Let me just move this down. Okay, so I'm going to take G0, which is this guy, and we also have P1, we compute their and then we need to also take this G1 here and compute the OR of all these 3 things, and this gives us C2. Let me stop here and make sure everyone is getting what's happening. The important point here is not like these connections or anything like that. The important point is for you to notice that C1 is completely computed independently from C2, once these G's and P's are computed. So you first compute G's and P's, and once that's done, everything becomes independent. C1 is independent from C2. And of course, you can compute the other ones in a similar fashion. It's just that these ands and ors that we have are going to get larger and larger. So for the first one, for the next one, I have to have, if you want it, so we have done C2 as, we have done C2 as well. If we wanted to do C3, now we have to do an AND of 4 things together. So we have to have C0 come in, we have to have P0 come in, we have to have P1 come in, and we have to have P2 come in. And P2 has to become available to the next one as well, so I'm going to take it there. That's just the very first term over here. Now we need to take this and this and so it becomes more and more complex. Let me also draw this one and then I'll stop. Okay, I'm not going to even attempt to draw C4 because it becomes a lot more complex. But I wanted to also to understand that as we go this way, yes, we are able to compute things in parallel. See, there is no, we're computing all of these in parallel. We just need these G's and P's. But this hardware gets more and more complex because now you need, an OR of 4 inputs, and you need an AND of 4 inputs, AND of 3 inputs, 2 inputs. That's for C3. For C4, it's even worse. You need ANDs and ORs of 5 inputs. So we can't continue doing this, but to the extent that we can, it's a good design. This C3, C2, C1, and C4, of course, are going to C1, C2, C3 are going to be fed to these, and so now the adders become independent from one another. This logic that we just saw is called a carry lookahead, a carry lookahead logic. It's also sometimes just referred to as CLA logic. And with this, you now can create a carry lookahead adder, which is also called a CLA for a carry lookahead adder. So what you do, I think you understand it at this point. You put that carry lookahead logic that we just designed in the previous slide over here. You give it all these A's and B's and C0. It generates for you C4, and it generates for you C1, C2, and C3 at the same time. And then you can do your 4 additions. These 4 additions are going to be now much faster than doing them in serial. We will do an example in the class that will establish that. If you wanted to create the 16-bit CLA, you could just ripple them just with it before, a ripple through. Now then you again have these dependencies. In the next video, we are going to see how we can get rid of those dependencies between these 4-bit CLAs.